Project 3.2.2, Program EEPROM by Atticus Tiplady. This is the second video in a series documenting the creation of the ACES CHUMP, which stands for Cheap, Homebrew, Understandable, Minimal Processor. The purpose of this project is to create an extension to the CHUMP as seen in Project 3.2.1, that is, the program EEPROM, which was created through the use of an AT28C16 parallel EEPROM and various other parts such as two 74HC595 shift registers. The portion of this project directly ties into the fundamentals of the program counter found within the first video. Hence, if there's any confusion, refer back to that video and then approach this one. The EEPROM in the CHUMP processor functions as a storage unit for program instructions, with each instruction encoded as 8 bytes, allowing for a structured sequence of operations to be delivered to the processor. Since the program counter only provides 4 address pins, it limits the EEPROM's addressing capacity directly to 16 unique addresses at a time, meaning that the processor can only access a subset of instructions within each page. To accommodate a full set of instructions, the EEPROM is organized into 128 pages, each holding 8 bytes of code per line. Moreover, since each page consists of 16 varying addresses, this means that in total, the EEPROM can hold 128 different 16-line codes, something very useful when trying to switch between different commands. The EEPROM, electronically erasable programmable read-only memory, is a type of non-volatile storage that keeps its contents after the power is turned off, in contrast to the volatile RAM, random access memory, which loses its contents when the power source is cut off. The EEPROM in this project functions as a storage unit for program instructions, with each instruction encoded as 8 bytes, allowing for a structured sequence of operations to be delivered to the processor. To get a sense of how the circuit works, we can look at the pinout of this IC. Similar to most chips, pins 24 and 12 are the voltage and ground pins, which can operate with a voltage range of 4.5 volts to 5.5 volts. An interesting thing about the AT28C16 EEPROM has to deal with its various address pins, with those being A0 through A10 found on pins 1 through 8, 19, 22, and 23. These address pins are used to specify the memory location for reading or writing data. With 11 address pins, the AT28C16 can access up to 2,048 to the 2 to the 11 unique addresses, each storing 1 byte of data, giving it a total storage capacity of 2 KB. This is due to the varying inputs possible. Therefore, when tied to a DIP switch bank, the combinations of highs and lows result in easy access to each individual address. Furthermore, similar to how other chips can read and write operations, the AT28C16 EEPROM employs control pins WE, OE, and CE to enable precise data management. The write enable pin, when low, allows data to be written to a selected memory address, while in a high state, it ensures the EEPROM remains in read or standby mode, preventing accidental data changes. Equally vital is the output enable OE pin, which, when activated by a low signal in conjunction with CE, outputs data from the selected address onto the data bus, allowing easy retrieval. However, when OE is high, the data bus is placed in a high impedance state, disconnecting the chip from the bus. Finally, chip enable, CE, controls the chip's readiness to operate. When low, it allows read or write actions as needed based on OE and WE conditions, while a high state places the EEPROM in standby, conserving power and securing data. Together, these control pins provide a streamlined method for managing memory access and ensuring data integrity across operations. Lastly, the final pins included within this chip has to deal with the 8 I/O pins found on pins 9 through 11 and 13 through 17. These pins are crucial in the CHUMP function, as not only do these pins act as an output, it also acts as an input, allowing the data stored in each address to change. These pins allow data transfer for both reading and writing operations, handling 8 bits, 1 byte of data at a time. When reading data, the I/O pins output the stored byte from the selected memory address, with the output enabled by setting OE and CE low. During a write operation, the I/O pins accept the data byte to be stored at the address specified by the address pins, with WE set to low to initiate the write process. Now, with the pinout out of the way, the purpose of this EEPROM within this project, as stated previously, is to store code that can be accessed later within this project. Looking at the circuit flashed regularly, you can see that the EEPROM is driving a 7-segment display and a 3D custom printed bar graph that is counted to 16 in hexadecimal. However, when the single-pull double-throw slide switch is active, the code switches into Feinberg's example code, showing a basic set of instructions the circuit follows. Furthermore, after the code flashes through it, it will flash 8 3 times to know that upon changing, the code is a new code that I have created, flashing 3 more times and then reverting back to Feinberg's. Looking at the circuit flash slowly, we can see that Feinberg's code matches with the one that programmed onto the EEPROM thanks to the inclusion of the bar graph. Each line does as follows: read to, places the constant 2 into the address register and advance the program counter by 1. Load. Load the contents of the RAM address into the accumulator, advance the program counter by 1. Add 1. Add the constant 1 to the accumulator, advance the program counter by 1. Store to 2. Store the contents of the accumulator into RAM at address 2 and advance the program counter by 1. Go to 0. Set the program counter to 0000, creating an infinite loop. Now this is a truth table for my specific code that follows after Feinberg's. Thank you for taking the time to watch my video on the RSGC CHUMP EEPROM.